In this video, I'm going to demonstrate how to calculate and interpret confidence intervals, and we'll do this based on samples, not from population parameters. This is a very typical exercise in describing our confidence in a particular estimate of an average or an arithmetic mean. I'm using the 2012 General Social Survey, and I've taken a subsample of black women who were asked the question, how old were you when your first child was born? This group of women were between the ages of 13 and 42 when their first child was born. The average age was 21.8 years old, and what we're going to do next is calculate a confidence interval to indicate how confident we are in that particular estimate. I'm going to remove this histogram so we can go ahead and calculate our confidence interval. What information do we need to calculate a confidence interval? We need three pieces of information. The first thing we need is the arithmetic average of our sample, which I said was 21.8 years old. The second thing we need is an estimate of the standard deviation of our sample, which in this case is 5.8 years. Finally, we need to know our sample size, which in this case is 151 black women. The sample size is important because with large samples we know we can use our typical Z or T scores of 1.96, 2.58, and 3.29 as we scale our standard errors. For small samples, we would have to go to a t-table and look up a number that will be slightly larger than any of those three numbers, depending upon our confidence interval. The first step in doing this is to calculate our standard error. The formula for the standard error is sigma hat sub y bar. Let's just take a minute to look at this. Sigma we know means a measure of dispersion like a standard deviation, and the hat means that it's an estimate of that. The y bar tells us what it's an estimate of, what it estimates, and in this case it's an estimate of the means. So sigma hat sub y bar is the standard error associated with a sampling distribution of sample means. We know that this is going to be equal to our standard deviation divided by the square root of n. And for this particular example, our standard deviation is 5.8, and we're going to divide that by the square root of 151, and we're going to get a standard error of 0.472. From here, all we have to do is now write out our formula for the confidence interval and solve. Our confidence interval, and here I'm using a 95% confidence interval, is going to be equal to our parameter estimate of the mean, so y bar, plus or minus our standard error, sigma hat sub y bar, times some kind of Z or T score. Going a little further, 21.8 plus or minus 1.96 times 0.472, which equals 21.8 plus or minus 0.93, and therefore our confidence interval extends from 20.9 years to approximately 22.7 years. That is to say, a 95% confidence interval for this problem lies between a lower limit of 20.9 years and an upper limit of 22.7 years, and we're fairly confident that the actual parameter estimate, while it's probably not exactly 21.8, falls somewhere in that particular range of values. And this range of values is driven by how wide that range is driven by how big our standard deviation is, which in this case it's not very large, 5.8 years, and that is by how homogeneous our sample is, and by our confidence, our sample size, and then of course by whether we're doing a 95, 99, or 99.9 confidence limit. Let's push on and look at a different example. Now I'm restricting my sample to, it's really the same problem, but I'm going to be looking at black women in 2012 who are divorced. And again, to calculate a confidence interval, we need three pieces of information. The first piece we need is our estimate of the mean, which is 21.6 years. Now you can contrast that with the last example when we had the sample of all black women. It was 21.8 years. And now we have a sample of black women who are divorced, and their average age at when their first child was born is 21.6 years. Our standard deviation for this sample is 4.7 years. And then our sample size is 8. So here we're confronted with a situation where we have an extremely small sample size. Anything over about 125, most statisticians will tell you can be considered a large sample. There's a little more complexity than that, but we can just use that number for now of 125. Less than 125, if I'm going to do a 95% confidence interval, I can't use a z-score like 1.96. I need to go to my t-table and look up the appropriate t-score. In this case, my t-score is going to be equal to 2.365. Here's our t-table. I need to look up my degrees of freedom on the left and look up whether I'm doing a one or two-tailed test in the appropriate alpha value on top, and then read into the table to find out my t-statistic. There's two ways to find the degrees of freedom here, the column labeled DF. The way I was taught was to use n-1, and since we have 8 women, n-1 would be equal to 7. So I'd come down and read across row 7. Some textbooks use n instead of n-1. I'm going to use n-1. For the purposes of this class, you can use either n or n-1. So I know that I'm going to come down and read across row 7. The next step is to look at the top of the table and see whether I'm using a one-tailed or a two-tailed test. All confidence intervals are two-tailed tests. And since I'm using a confidence interval of a 95% confidence interval, I need to come across and use this 0.05 column under the two-tailed test heading. So now I know I'm reading across the row labeled 7, and down the column, this column labeled 0.5, and I come to my t-statistic, 2.365. Again, for this course, it would be okay if you used 2.306 for 8 degrees of freedom. So now we can just go ahead and solve again for our standard error, our estimate of the standard error, which is equal to our standard deviation divided by the square root of n, which is equal to 1.66. Notice that this standard error is larger than the last example, as you might expect, because we only have 8 women instead of 151. So a much smaller sample size, and we know as our sample size becomes smaller, our standard errors get larger. We solve for our confidence interval the same way we did before. That is, we're going to have an estimate of our mean, in this case 21.6, plus or minus some z or t-score, and our t-score here is 2.365, and we'll multiply that by our standard error. And in this case, our lower limit is 17.8 years, and our upper limit is 25.5 years. Notice that this standard error and this confidence interval, while it's still a 95% confidence interval, is a lot larger than the one in the first example. And we have approximately the same standard deviations, approximately the same means. Really, the big difference between these two problems is the standard error is larger because of the smaller sample size, and the t-score is larger because we have a small sample size. So again, in doing these kinds of problems, sample size is one of the important factors to consider when you look at your confidence intervals.